Hello, and a very warm welcome to everyone joining us for today's Select Science webinar entitled Pressing Matters, a guide to sample preparation for XRF, FTIR, and more. My name is Sarah Thomas, and I will be moderating today's presentation. I am delighted to introduce today's speaker, Will Campbell, Technical Insight Coordinator at SpecAC. Today, he will discuss the basics of sample preparation for XRF, FTIR, and other analytical techniques requiring pelletized samples. Will also cover how you can overcome some of the challenges associated with pellet pressing and the different pressing equipment available. Just before I hand over to our speaker, I would like to mention a couple of things. Please feel free to ask any questions for the Q&A session at any time during the webinar by clicking on the Ask a Question button at the bottom of your screen. You can also view the presentation in full screen by clicking on the tab at the bottom right of the media player window. Finally, an on-demand version of this webinar will be available in a few days' time if you would like to watch it again. So without further delay, I would like to hand over to Will for today's presentation, and I would like to thank him for presenting to us today. Please go ahead, Will.
Thank you very much, Sarah. Well, welcome everybody. As Sarah has already ably pointed out, we're going to look at a few applications of hydraulic presses in the laboratory today via a couple of different analytical techniques. The first is X-ray fluorescence spectroscopy, or XRF. The second is Fourier transform infrared spectroscopy, or FTIR. And we'll also look at a couple of other uses of hydraulic presses in the laboratory that aren't necessarily to do with spectroscopy, but perhaps more engineering-based. And at the end, there'll be a short summary and a time for questions. So, XRF spectroscopy. It's an extremely common technique in numerous industries. It's an atomic spectroscopy technique, which means it looks at the elemental composition of your samples. It's used in metal and mining industries, very prominently in all kinds of mineral ores, metal production, furnaces, livestock feed, pharmaceuticals, lots and lots of different things. So, why might we want to prepare samples for XRF spectroscopy? Well, I think it helps to understand how the technique works. So we've got here a drawing of an atom with a nucleus surrounded by several electrons arranged in shells in ascending order of energy, from the K shell with the lowest energy all the way through to the L, M and N shells with greater energy. Our spectrometer will bombard the atoms in the sample with X-rays, and they will liberate electrons from the lowest energy shells. And we've got here an X-ray coming in and interacting with one of those lower energy electrons. And the effect of that will be to eject the electron, like so. This leaves our atom in an excited state, and one of the ways it can relax from that state is if another electron, say in the L shell as shown here, drops into the vacancy left by the electron that was originally in the K shell. And in doing so, it will have to emit some energy, and that energy will be equal to the difference in binding energies between the two shells, like so. And that released photon, the energy comes out as a photon, that's our analytical signal. Now, if the electron dropped from, say, the M shell, there would be a different amount of energy, and if it dropped from the M shell into the L shell, there would again be a different amount of energy, and this gives every atom a characteristic series of emission lines. And we can quantify the amount of atoms in a sample, or the proportion of elements in a sample, by comparing the intensity of certain emission peaks with a calibrated standard. Unfortunately, it's not quite as straightforward as that. It's well known that there will be all sorts of other interactions with both the exciting X-rays and the emitted X-rays that we're looking for. There will be interactions between different elements in the sample. And it's also well known that the physical presentation of the sample itself will lead to scattering and other effects that will reduce that proportional relationship between the emission intensities and the quantity of elements in your sample, and may make it even harder to see certain types of elements. So our ideal sample for XRF analysis is actually prepared in some way to help us with this. We want our sample to be completely homogeneous, or homogeneous as far as possible, and that means no variation in particle sizes, composition or voids. We want to make sure those particles are as small as possible, because the boundaries between grains can interfere with the result. And because XRF is primarily a surface technique. It's very, very sensitive to just the first few microns of the surface. We want the surface of the sample itself to be perfectly flat and smooth. We don't want any variation in distance to the detector, and we don't want any scattering introduced at the sample surface. Now, depending on what type of sample we have, there may be various ways that we can achieve this. If you've got a bulk solid, such as a metal, you could just cut a fresh surface and polish it to a very fine degree and use that. And likewise, if you've got a liquid, liquids tend to form nice smooth surfaces anyway, so you can put it straight in a cup and analyze it directly. But a lot of samples are in powder form. They're either natively in powder form, if you're dealing with a pharmaceutical compound, for example, or they can be ground into powder form with various crushers and milling machines. And that would be the case with mine tailings, for example. And it's powdered solids that we're going to look at a bit further in this presentation. We can analyze those powders loosely in a cup, but we're not really advancing towards improving the quality of our results if we do that. We're not improving the homogeneity of the sample. We're not reducing the grain sizes. So really we've got two options. One is a pressed pellet, where we use a hydraulic press to compress our powders into a solid disc. And another is the fused bead technique, where we mix our sample with a flux of some kind, raise it to very high temperatures, typically 900 to 1000 degrees C, and then pour it into a cast and allow it to cool down and form a glass disc, or a fused bead as it's known. And there are pros and cons to both of these techniques. Pressed pellets are generally compatible with a wider range of sample types, but fused beads go as far as you can possibly get to remove all of the heterogeneity in your sample. However, there are differences in cost and speed as well. A pressed pellet is generally faster, so if you want fast feedback on a process that you're monitoring, you may want to have a pressed pellet. And you also want to consider the extra cost of your fused bead sample preparation, the fusion heaters that are required, and the platinum labware. Look at a particular example of XRF sample preparation. We're going to look at glass in the glass industry. Glass is a form of fused silica, basically just sand, but it often contains other materials that act as stabilizers or colorants. So things like sodium sulfate or various metals such as iron and chromium that would impart color to the glass. And XRF is really ideal for measuring the concentration of these additives, both in the final glass product, but also checking for impurities in the ingredients themselves. We don't want to put anything into our glass that is going to hamper the actual glass making technique or corrode the materials used to make it. So in this example, we're going to look at 3 pressed pellets, and those samples are photochrome, which is a colorant, limestone, and sodium sulfate. We're going to press those as pellets. And then sand we're going to make into a fused bead. And here they are. So I've labelled this up for you. You've got the sand fused bead on the left, and then the 3 different pellet samples on the right. And one thing that's worth pointing out here is that although there's different terminology, you've got a fused bead on one hand and a pressed pellet on the other. They are both just circular discs, so don't be overly confused by the terminology. They're very different techniques, but the result in physical form is not so different. The general steps for preparing the pellet samples were as follows. We took the raw material, ground it using a planetary ball mill. We used 20 grams of raw material. You want to get the fineness of the powder down as far as possible. You want to have the smallest grains you can have, and you want consistent size. Remember that we want a homogeneous sample. Practically, you can get down to around 20 to 40 microns, depending on the sample you're using and the equipment. And if you have the time to go on grinding for much longer, perhaps for several minutes or even longer, up to an hour, then you can reach higher fineness levels. But practically speaking, you probably want to prepare your samples faster than that. The next stage is to mix the samples with a wax binder. In this case, we've got around 1 gram of wax binder for every 5 grams of sample. And the reason for this is that not every sample will actually form a freestanding pellet. It won't necessarily form into a solid when you compress it. So if we add a bit of a waxy material, we can improve the adhesion of those particles and make sure that we get a nice smooth pellet surface. And those are milled for a further 30 seconds just to thoroughly mix them together. Then we transfer our prepared sample to the pellet die, and there's an example of one of those on the top right-hand side of the screen. It's just a cylindrical object with a plunger. The first thing that goes in this case, is a layer of boric acid, which just acts as a substrate. We're not going to measure that. And then we pour in our sample, our mixture of sample and binder. Place the plunger, move it into the pellet press, which is shown on the bottom right. Clamp it between the platen and the bolster there. And then we use the lever on the right-hand side to crank up the pressure all the way up to 25 tons and leave it for a period of time to let the sample settle. And then when we think it's done, we remove the pellet from the die and take it to the spectrometer. And we end up with results somewhat like this. The spectrometer will automatically label the results. We're showing here the sodium sulfate and the photochrome samples. Unsurprisingly, the sodium sulfate contains a lot of sodium and sulfur and a few other things, while the photochrome appears to be composed of various kinds of metals such as iron, vanadium and chromium. It's quite difficult to lay down general principles for XRF pellet preparation. Every sample will be different. Some pellets may be self-supporting, so you can put your powders straight into the die as we did with our glass samples, and you'll get a nice freestanding pellet. Others may require a bit of additional support, so what you can do is use an aluminium or plastic sample support cup, and there's a little picture of those stacked up on the top right there. These are just deformable dishes that go into your pellet die before you put your sample in, and when you apply pressure, they fold themselves around the sample and leave only a nice smooth surface exposed for analysis. Typical pellet diameters are 32 or 40 millimeters, and that's really dependent on the spectrometer that you're using. Most spectrometers have a sample introduction system, so you do need to check what size pellet is required before you purchase any dies. Now, we used a manual press in the last example, and that's fine. You apply the pressure manually. It's up to the user to make sure the pressure is applied exactly and that the loading is maintained for however long is required, and then to release it appropriately. But really, you're looking for a magic formula for every one of your samples. You don't know exactly how quickly you need to ramp up the load, what the load required will be. You don't know whether you need to leave the sample at full load for just a few seconds or perhaps several minutes. And so you're going to have a lot of experimentation involved, and it helps that once you've stumbled across your magic formula, if you have some way of storing that program so that you can use it repeatedly. And that's where these semi-automatic programmable presses come in. The hydraulics here are power operated, so there's no hard physical labor involved in cranking up the pressure. And you can store every program that you make. So you can have several steps. You might want to ramp up the load for say halfway, let the sample relax or any gases that are contained with it come out, and then continue loading. And if you want to hold the load for a particularly long period of time, the fact that we're using automatic controls here enables us to add all sorts of features, such as automatic top-up of pressure to make sure you don't lose any pressure in the system, and also features that help you remove the pellet quickly from the die when you're done, a push-out feature as it's called. And of course, if it's all automated, you're spending much less time in front of the press and you're freed up to go and do other things while it's running. And in this way, you can be guaranteed of consistent and repeatable sample preparation no matter who is using the press. So moving on to Fourier transform infrared spectroscopy, if anything, this is an even more ubiquitous technique than XRF. It's a molecular spectroscopy technique, and it's used on all kinds of powder, liquid, gaseous samples. And we've just got a few here on the screen just as examples. We've got some polymer beads, we've got some amoxicillin, which is a pharmaceutical active ingredient, and some powders. Once again, why do we want to prepare samples for FTIR? Well, how the technique works is that we're shining infrared light on our sample, and particularly in the wavelengths between 2.5 microns and 25 microns, which corresponds to wave numbers of 4,000 to 400 reciprocal centimeters, we're going to get a lot of interaction between the sample and the infrared light, and we get very distinctive absorption features that help us identify the sample in question. The absorbance is related to the concentration of the absorbing species in your sample and the path length. And we need to very carefully manage the interaction between the infrared light and your sample, because otherwise your sample will absorb all the light and nothing will reach the detector and you'll have no signal to analyse. Now for powdered samples, once again, one of the ways of preparing your sample is to disperse it in an infrared transparent medium such as potassium bromide, or more commonly known by its chemical formula, KBr. When we do so, we dilute the sample, change the concentration that is interacting with the light, and by pressing it into a disc we form a nice convenient solid that we can use for analysis with a fixed path length. And typical conditions for that preparation I've shown here on the slide. Normally it's around 100 parts KBr to sample by weight. Very, very commonly a 13mm pellet die, 10-ton pressing loads. It's very standard and works for a very wide range of samples. There are, however, still some pitfalls for the unwary. You might find after removing your pellet from the die that you've got visible lumps or inclusions, or the sample looks cloudy or opaque. And of course the acid test is the actual spectrum that you take. If you find that the transmittance is very low, or you have very poorly resolved peaks, or other spectral features that you're not expecting to see, then you may have to go back and look at your sample preparation steps. So some common causes: number one, the KBr itself is damp. Potassium bromide absorbs moisture from the atmosphere very readily, so you need to keep it dry. And when it is damp, it doesn't mix well with your sample. It's very difficult to grind your sample thoroughly into your KBr matrix. And while mentioning grinding, inadequate grinding is another common problem. You want to make sure that you're properly mixing your sample so that you don't get small lumps of sample in your pellet. You want to make sure it's fully dispersed in your matrix and have no additional lumps or clumps that shouldn't be there. And a few others: uneven felling of the pellet die. And also, if you're not weighing your sample accurately, then you're going to end up with concentration too high or too low. And here are some examples. This is just an ibuprofen sample. We expect it to be a dry powder. We've got two spectra here of less well prepared samples. So on the top in the red, we've got an example where the concentration of the sample was too low. We didn't measure the proportions properly. We've got high transmittance, so we're getting a lot of light through to the detector, but we're not getting well-resolved peaks because we just don't have enough concentration in the sample. Whereas at the bottom in the black line, we've gone the opposite direction. We've got much too much sample. The peak transmittance, even in these regions that don't absorb, is only 50%. We're getting a lot of scattering of the light. But we've also got, and I'm marking it on here, a large water absorption feature at around 3,400 wave numbers, and this tells us that the sample itself has absorbed some moisture, and we haven't properly dried our sample. So what does a perfect pellet look like? Well, it looks like the blue line above. Once again, we've got in black the previous spectrum with the water absorbance, but the blue spectrum you can see has got much higher absorbance. If you look at the region between 2,200 and 2,000 wave numbers where we're not expecting any absorbances, we've got very high transmittance of almost 90%. The water feature is greatly reduced, and we've got nice, easily discernible peaks that are well resolved in the fingerprint region on the right-hand side below around 2,000 wave numbers. Now, something you might want to think about if you're making lots of pellets as a routine for FTIR spectroscopy is that although the standard size has often been 13mm, for which you require a 10-ton load, anyone who's ever actually done this will know that as you get up towards 10 tons, the amount of effort you need on the handle of the manual press is rather a lot. And it actually takes quite a long time to build the pressure up to 10 tons. But you can actually get an acceptable pellet of 7mm, so around half the size, with as little as 2 tons. So now available, we have these mini pellet press devices where all you need is to turn the handle that you can see on the front there to apply a load. You get up to 2 tons very quickly and very easily with the minimum of effort. You can prepare more samples this way, and for FTIR spectroscopy, a 7mm pellet is more than adequate. And in actual fact, the spectra that we were looking at just a few moments ago, including the perfect pellet, were made on exactly such a device. I also promised that we'd look at some applications beyond spectroscopy. So you can also use a hydraulic press, of course, to just compress materials. Some examples are here. You might want to make some ceramic materials that are reinforced with other materials, say, for example, nanocomposites. You might want to make composite materials of other kinds. Nuclear fuel pellets. In nuclear fuel applications, you want to make sure that you're making a nice solid pellet that doesn't come apart under the high stresses and temperatures involved. You might also, if you're developing new oral dispersions in pharmaceutical research, and you want to just make a couple of tablets, rather than use full-scale tablet production facilities, you could make a pellet for testing in a laboratory press, on a benchtop press. And no matter what kind of sample you're making, you can go and then do all kinds of testing subsequently. So you measure the hardness if you're making a new composite, or the density. You can measure the thermal properties of a nuclear fuel pellet. You can measure the dissolution in the simulated stomach contents of novel solid oral dispersions in pharmaceutical tablet production, or the wettability of that pellet. And you might also just want to test materials for other sorts of properties, and an example of that would be material testing for the print industry. Ink manufacturers have to test all of their inks for a phenomenon known as blocking, and this is where the printer has produced a whole load of printed materials, stacked them in the corner, or rolled them up into a roll or a drum, left it on the shop floor, and they find that with the pressures that develop between the individual sheets, ink is transferred off the printed page and onto the adjacent sheets where it's not wanted. And you can test the likelihood of this blocking phenomena occurring on all sorts of different paper mediums by simply preparing a specimen, a test specimen, stacking them together and applying a load on them using a manual press for a period of time. And you go back to your sample after several hours and look to see whether the ink has in fact blocked or not. And you can set up a standard procedure, and if it passes, it passes, and if it doesn't, it doesn't. Last but not least, you can extend the power of your press by adding heat. Heated platens are available for all presses. You can have temperatures up to 300 degrees, and this is particularly useful in the plastics and polymer industry, where you might want to make an infrared transmission measurement of a film, not in the pelletized form of your plastic, but in something close to the final product in compressed and extruded form. So we've got various equipment that will help you make a film of a set thickness for your transmission measurement, so you understand the path length that's involved. And again, heating up to 300 degrees or even more is available for these products. So just to quickly overview the products and the techniques that we talked about, there's a huge flexibility in pellet dyes no matter what your application is. If you're doing XRF and you want to avoid metal contamination, such as iron in the stainless steel body, there's option to have tungsten carbide pressing faces in contact with your pellet surface. You've got diameters from 5 to 40 millimeters. The smaller diameters typically associated with FTIR, and the larger 32 and 40 millimeter sizes typically with XRF, but you might want to have very high pressures and high loads, for example, in the smaller dies. And again, a range of presses. We've looked at the standard manual press. Very, very simple, easy to use, rugged. You can't really go wrong with it, but if you're making routine samples at high load, you might want to consider the 2-ton mini pellet press for regular FTIR sample preparation. And if you want truly consistent sample preparation, irrespective of who's using the press, and you want to make sure that you don't lose any of the benefits of the experimentation you've been doing in ascertaining the right sample preparation procedure, then a semi-automatic programmable press is exactly what you need, and the Atlas Autotouch is a great example of that. And finally, we spoke about pre-preparation of the samples, grinding particularly. You can get planetary and vibratory ball mills to grind your samples down to a final fineness of as little as 50 or 40 microns. Aluminium sample cups, these sample support cups that help you hold together loose powders when you press them. Liquid cups for holding liquid samples. Various binding, grinding aids and additives that will help you ensure that your samples form into nice homogeneous pellets. And then supplies for FTIR as well, including sample cards and potassium bromide powder. So in conclusion, with the techniques themselves, remember that for XRF you want smooth, homogeneous samples, and that pellet samples are an extremely effective way of achieving this for a very wide range of sample types. And if you want the most consistent pellet preparation, use a programmable press such as the AutoTouch. For FTIR, make sure you thoroughly grind and properly weigh your sample, and keep your powder dry. The KBR doesn't take kindly to grinding if it's damp. And of course, you can use your presses for a range of other techniques, whether it's material testing or preparation of composite materials, not just for chemists, also for engineers and material scientists. Don't forget to visit our website for helpful hints and tips. We've always got new content going up. Got 6 tips for the perfectly pressed XRF pellet here. There's a recent one. And of course, keep an eye out for any new products that may be released. I think that's all. Thank you very much for listening. I hope you found it useful. You can connect with me using the contact details shown or visit our website, as I've already mentioned. And next week in Big Sky, Montana, we will be at the Denver X-ray conference with all of our sample preparation equipment. So if you're going to that, do stop by and say hello. Thank you very much, and I'll now hand you back to Sarah.
Thank you, Will, for a very useful and interesting presentation. So now let's move on to the final part of today's webinar, the question and answer session. So our first question is, what are the range of tonnages typically required for XRF?
Thanks for the question. This is basically sample dependent. If you've got a very soft sample, for example, a milk powder in the food industry, you don't need very much load. You might need only 2, 3, 4 tons, something of that order, and our sort of 8-ton AutoTouch presses would be ideal for that kind of analysis. And also, those samples tend to hold together really well without binder. Whereas if you're analysing something like cement or iron tailings or something of that order, where you have something a very, very hard and brittle sample, those sorts of samples don't bind as well, and you need a binder, and you might need a lot of a very high pressing load, let's say 40 tons, which you could do with our 40-ton press. So it's essentially sample dependent.
Great, thanks, Will. We have another question. Are there maximum load ratings on the pellet dies themselves?
Yes, there are. So it depends on the size of die. If you have a 5mm die for FTIR analysis, for example, then you can only load that up to 2 tons, whereas all of our XRF dies are rated all the way up to 40 tons to be compatible with our top range of presses. But you do need to be very careful that depending on which combination of press and die you're using, it is possible to overload the die. So always check the load rating on the die before you use it, and make sure you buy a die that will be compatible with the press you're using.
Thanks, Will. And we have another question. When would you use fusion beads versus pellets?
Oh, this is a very interesting question. Generally speaking, as I said in the webinar, you want your sample to be as homogeneous as you can get it, and you want the sample surface to be as smooth as possible. And pressed pellets are a great way of doing that for a very, very wide range of samples. You can use it on almost anything, whether it's plant matter, soil, something like titanium oxide used in the pharmaceutical and cosmetic industries, cement, iron tailings, all of those sorts of samples. And the great advantage of it is that it's very, very simple and fast. So if you're monitoring a process, then you'd always want to use pellets over fusion beads simply because of the time scales involved. But there is one particular effect that's seen in Xrf spectroscopy known as the mineralogical effect, which is quite complex, but it's basically when you have the same element stored in different mineral structures. That can make it difficult to quantify your samples. And the advantage of fusion beads there is that it completely destroys the mineral structure because you're heating it to such high temperatures and removing all of the crystalline structures. But that has to be balanced against the risk of when you heat your samples, you might have elements boil off or evaporate away, which obviously you don't want if you need to measure that sample. Of course, there's a sort of cost and time implication. You've also got to remember that you're diluting your sample with fusion beads. So if you have a trace element that you're trying to look at, then it might not be desirable. Okay.
Thank you, Will. We've got time for one more question. Can you comment on an XRF sample prep technique for plastic pellets, which are usually hard at room temperature and melt above at much higher temperatures?
There are a large number of ways that you could probably do this, and I think it's probably better if we discuss this offline. So I will email you a fuller answer to this. But I think the strategy would depend on exactly which pellet you're using and on its melting point. One thing you could do, I mentioned very briefly there, the heated platens. You might be able to make a thin film using a constant thickness film maker and heated platens, and to just make a small 30mm sample that you could then use on your XRF machine. But there are other ways that you could do it, and I think I will send you some literature on that.
Great, thank you, Will. Well, that's all we have time for today. So thank you very much to Will for today's informative discussion and presentation, and thank you to everyone joining us online and for your interesting questions. I hope that you found this a worthwhile session. If we didn't manage to answer your questions, please feel free to email me at sarah@selectscience.net, and I will follow up with your questions for Will personally. If you would like to listen to today's webinar again, or to invite a friend to listen, it will be available to watch on demand in a few days' time. Goodbye, and thank you once again for joining us.